Chapter 13, all about liquids. Alright, so we've learned a little bit about pressure from learning about solids in Chapter 12. Now we're going to take that and look at it in liquid form, talk about buoyancy, Archimedes' principle, flotation, Pascal's principle, and a little bit about surface tension and something called capillarity. Alright, so to begin with here, pressure. Pressure is force over area. Okay, so how much force you got applied over how much area, that gives you pressure. Alright, pressure is measured in newtons over meters squared, which is the same thing as a Pascal. Okay, so if you see either of those, you can know how to handle them. Pressure and force are directly proportional. You increase force, you increase the pressure. What area is on the bottom of this fraction, so inverse relationship, right? There's an example of pressure. It looks painful, but read about it. It's kind of cool. Alright, pressure in a liquid. Alright, pressure is always force over area, as we discussed. However, if you have an object like this person diving in the pool, if they're submerged, then they're going to feel that pressure on all sides, but they're going to feel more pressure with depth. Because yes, pressure is force over area, but what's supplying the force? Well, the weight of the water above you is supplying the force. So the deeper you go, more weight of water above you. Alright. Now, you may have heard the phrase, water seeks its own level. Right? Because what it's doing is it's leveling out due to pressure. And again, pressure depends on depth. So no matter what kind of funny shaped container you have, like here, pressure is the same because it depends on the depth, right? That's why these two fish here in the picture will feel the same pressure. Now, if I have a cup like so, and I poke holes in it, how fast is the water going to spurt out? Well, again, that's a direct relationship to pressure. The more pressure, the more push behind it, the more speed the water's going to have when it squirts out of the hole. Hence, the bottom hole here will have the biggest speed. But no matter what the speed or where the hole is, it will always be perpendicular. The water will always come out of that hole perpendicular to the container. Buoyancy. Buoyancy means floating or able to float. Right? Liquids and gases are called fluids, and fluids have buoyancy to them. Ever notice how something feels lighter in water? Well, that's the buoyancy helping you to lift it up. Alright? Another way you can think of a buoyancy is feeling lighter in water gives an idea that the object kind of lost weight. But we know they didn't really lose it. But this apparent weight loss is related to buoyant force. Alright? Now the difference between the upward and downward forces acting on any submerged object is the buoyant force, right? So if you have a force pushing down and a force pushing up, see how you got two arrows on the bottom, one arrow on the top, giving you a difference of 1, right? If you look at this block on its trek down to the bottom of this pool, you'll see that the difference will always stay 1, right? Buoyant force is consistent. It doesn't matter if it's submerged near the top, middle, bottom. Buoyant force depends on the difference in those forces, right? And how much water gets displaced. And we'll talk about that in just a second. Alright? See, here's an idea to know whether the object will sink, float, or stay at some level in between. Okay? Now, that water displaced that we were talking about, here we've got a weight, and it looks by this scale, it has a weight of 3. Alright, we've got a little catch can in here, because where we filled this beaker up to the top, we deposit this mass in there, it's going to overflow, right? Well, now it seems like this block weighs only a unit of 1. So it seems like it lost 2 pounds, or 2 units, or whatever this is measured in. Well, guess what? That's the amount of water displaced. Right? So however much water gets displaced, Alright, that weight is equal to the buoyant force. Right? So buoyant force acting on this weight in the water is 2. Alright. So buoyant force being equal to the weight of the water displaced is the first part of Archimedes' principle that we're going to talk about. Second part is flotation. Right? So we've got a block of iron here, put it in the water and it sinks. But if we can somehow stretch that iron out and make it like a bowl, well then it'll float. Well, what's the difference? Why one and not the other? Well, one is going to displace a greater amount of water, right? So this boat displaces more water than this block right here. So displacing more water means there's more buoyant force. Well, why is there more buoyant force now? Well, look at the volume. The volume got spread out, so now we've got this whole bottom of the boat as a place for that buoyant force to act. Where over here, we only had this much space for the buoyant force to act. Alright, so spreading out that volume gives buoyant force a little extra time to work. Alright? So density. Here's how density can affect that buoyancy. Right? If you have a denser fluid, alright, then that won't depend on how well the object sinks or floats. Think of this drastic example. If you have a pool of water versus a pool of jello, right? Jello is denser than water. You're most likely going to sink in the water, but you'll stay on top of the jello, right? So density plays a factor, and there's some points for that. Alright. Pascal's principle. Pascal noticed that if you enclosed a fluid, right, just like in this tube, see we got these tops on it, so it can't go anywhere, it's enclosed, and then you applied a pressure, well that pressure is going to be transmitted through every little point in this tube, and it'll be felt over here. So whatever force is applied here, creating a pressure in this fluid, is going to be the same pressure and force felt on this other side. Alright, that's pretty cool. And we can take that idea, and then if we make the two sides of the tube different, look at that. Now we just increase the area by 50%. All of that force is still getting distributed to every little particle, every point of fluid in there. And now it's got a 50 area 50 times bigger to act. Well, it can now lift the supply of force 50 times greater. Right? That's the whole idea behind hydraulic lifts that you see in mechanics offices, garages. It's pretty cool. Surface tension. Right? So here's a picture of what I mean by surface tension. Right? You put a paintbrush in water, it spreads out. You pick it up out of the water and then it closes back up. Right? What makes it close back up? Well, that's the molecular attraction between the water molecules going and sucking that back in there. Alright, now if you've just got water in a cup or water on top of a lake, right? Well, it doesn't have as many neighbors, right? It only has neighbors on the bottom sides, right? So beside it, left and right, and then on the bottom. Where if it's a molecule of water down at a certain depth, it's got neighbors all around, right? So it's got some molecular attraction going on everywhere. Here, only molecular attraction on this bottom side. Alright, well that makes these top molecules pull together even harder. Alright, and that creates surface tension on top of the water. That's what lets those little water bugs run across the top of the water. And so it makes something like a paper clip or a piece of paper float for a bit. Surface tension. Alright, that surface tension can also be related to drops and bubbles. Alright. The reason why drops of rain, as you can see here, or bubbles, as you can see here, are spherical is because that gives them the greatest amount of volume for the smallest amount of surface area. Alright? And that's just how the molecular attraction works. All these on the outside, ball them up. Alright? Capillarity. Alright? You ever get a drink, soda, at a restaurant, and the next thing you know, it's spilling out of the straw and you didn't even do anything? That's capillarity. You have a change in pressure, and it draws that fluid up the straw. That's capillarity. That's the same way that wicks in like oil lanterns work. That's the same way if you've even, girls, got your hair piled up on your hair, but you got a few little straggles down here, and you lay back in the tub. When you get out, you're thinking, how'd my hair up here get wet? It sucked it right on up. That's capillarity. Alright? So how does it even out? When does it know to stop? How high will it rise? Alright? Well, if you've got something like a straw or tubes as seen in this picture, it depends on how big the diameter of the straw is, the force pushing down on the water, how much it'll push up in there, right? But when the pressure here in the dish equals the pressure in the straw, that's when it stops rising. Okay? So you have some neat videos to watch with this one, some fun examples that I hope you try for some extra credit points. And as always, if you have any questions, let me know.